All right, so let's pick up where we left off on whatever it was, Friday, I guess, where we were super close to finishing up the notes for the year. So we had talked about torsion pendulums. Remember that we spent a pretty good chunk of time deriving in two different ways, deriving this equation for the period of a simple pendulum. And it doesn't say it here explicitly. I guess I probably should have said that this was for a simple pendulum. All right? All right? So, everybody good up to there? All right, we're going to need to come back to this derivation here in a second. So, let me see where we're at. Yes, we did that. That's all the stuff we did the other day. Okay, so the last thing, I think that for the last two things we need to talk about, one of the last two things we need to talk about is what's called a physical pendulum. All right? So the equation that we derived the other day was the equation, I know it's an unfortunate thing, if that's what you're talking about. Simple pendulum. So a simple pendulum is a pendulum in which the size of the mass, it's a point particle pendulum. Is that enough of an explanation?
Yes.
Okay. So, and so in that case, the equation is 2 pi root L over G. L is the length of the pendulum, G is acceleration of gravity. All right? But frequently we have something that's a little bit more complicated, right? Like what if I made a pendulum out of this guitar, right? And I wanted to find the frequency at which this guitar oscillates back and forth. Okay? So, there is an equation for it, all right? So, here's what the equation is. So it's the period of what's called a physical pendulum. It's 2 pi times I, where I is the rotational inertia of the object around, your obvious pivot point. And then it's divided by mgh, where h is, and I don't know if it says this anywhere in the notes, so you might want to write this down. H is the distance from, oops, that is not how you spell from, the pivot point to the center of mass. So it's kind of the same as the h in the parallel axis theorem. Cool? So where does that come from? I'm not going to go through a whole derivation. I'm going to point to a thing and I'm going to go, it comes from right here. All right? So, here's where it comes from. On Friday, we derived the period of a simple pendulum by looking at the restoring torque. And it was this. Okay, T is 2 pi square root of I over K, and we'd figured out that I was the force of gravity times the length. Because that was, how did we end up with that? Oh, from up here. Because our constant, our torque was proportional to the displacement, right? And so our constant was FGL, and the L was a result of the length of the lever arm for your torque. Okay? So here we just replace the L with H, and it gives you this new equation, which is right here. Okay? So literally, it's so all I did is I replaced the L with an H in that restoring torque solution that we did the other day. Cool? All right. This is another one of those things where I would be surprised if this showed up on the test. It could, but it's such a specific equation, and the derivation for it is not easy. This equation is not on your formula sheet, so to me it doesn't seem like a thing they would put on there. And it's in the curriculum, so we should do it real quick. All right, so I think probably the easiest way to do this is an example. So here's an example of a physical pendulum. All right, so basically what the physical pendulum is here is it's 2 meter sticks joined together like this. All right, and then the pivot point is where they intersect, and so then it's setting to oscillating like, I can't do it because they're not actually tied together, but it's doing this. Make sense? All right, so our goal is to find the period of oscillation that this would experience if I, actually did it instead of just holding it together with my hand like this. Follow? All right, so we're just going to use this new equation, 2 pi squared root of I over mgh. So we need to do a couple things. One, we need to find I. So we've actually got two pieces. We've got one piece that's oscillating like this, and one piece that's oscillating like this. So how do I find the rotational inertia of the combined thing? You find the two individual things and add them, right? Okay? So, for the piece that runs this way, I is 1/3 times the mass times, what? You guys remember? If they're literally meter sticks, what number would I use? Is it 1 squared for the top piece? It's half, yeah. So when your pivot point is at the center like this, it's 1/3 ml squared, where L is the length from the center. If you use the whole length, then it's 1/12. Okay? Cool? So that gives you 1/12 m, right? Because this is a fourth times a third is a 12 times that. Good? All right? And then this piece, the vertical piece, has I of 1/3 m times, now you use the whole length. Follow? All right? So that means that the I for the whole thing is the sum of those. So 1/3 and 1/12 is what, 5/12, I think? Follow? All right, so there's the rotational inertia of our shape. Now, what's the other thing we need to find? It's 2 pi times the square root of I over mgh. So what's the other thing I need to find, you guys? H. Right? Hopefully the m's will cancel. So what does H represent? The distance from the pivot point to the center of mass, right? So here's my shape. So this top piece has a mass of m, and this middle piece has a mass of, or the vertical piece has a mass of m. So if I want to find the height of my center of mass, and I call this the top a height of 0, do you guys see where this is going or no?
Yeah.
So tell me what to write. To deal with the top piece, I'm going to use, you guys remember how to find the center of mass? xm plus xm over the total mass. I'm going to put that on the ground. Good, so it's this top mass times the distance of 0, right? Because it's already at a height of 0. Plus m times a half, right? Because if this is 1 meter, then the center of mass of that 1 meter stick is half a meter, right? All over 2m. Does that make sense or no?
And that's 0.25.
That m there is meters. The other m's are, all the other m's are mass. That m is meters. Good?
So is that center of mass 0.25 from?
From the top. So I'm calling this a height of 0 and then measuring down.
Okay.
Right? That was why this was 0. Does that make sense?
Yeah. Yeah. So you can think of it as negative 0.25.
Yeah, sure.
All right.
Sure. All right, everybody good? Problems? All right, so if I go back to my equation over here, it's square root of I over mgh. So, oops. Oh my gosh. There we go. All right, so I is 2 pi times the square root of I over mgh. Now, you got to be careful here. When I wrote this example up, I made a mistake, and you got to be careful you don't make the same mistake. All right, so it's 2 pi times the square root of, what did we decide I was? 5/12 m.
Oh, T equals 2.
Oh, shoot, t, thank you. Holy cow. Thank you. T equals, thank you. Sorry, if you missed that here, that's T. I think I had it as I before. All right, over mgh, right? What does m represent here? What does m represent? The mass of the pendulum. What's the mass of this thing? 2m, right? Because there are 2 meter sticks, right? So 2m g times h, we decided was 0.25, right?
Wait,
Follow? All right. The m's cancel out, and then it's just plug and chug, and you get whatever I said the answer was on the example sheet. What's it? Is it 1.83? Is that right? Yeah, 1.83. Good? All right, one last thing, and then a quick demo-y thing, and then we're done. All right, so is everybody good up to here? All right, now, another thing that you need to be aware of, though this is probably the last new thing that we're going to learn. Center of oscillation. So if you go back to, oh shoot. Here we go. Nope. Here we go. So if you go back to this page, you guys, right here, it defines what's called the center of oscillation. All right? The center of oscillation represents a point at which you could concentrate all of the mass to get the same period. In other words, if I wanted to replace this pendulum with a simple pendulum that had the same period, then how long would that pendulum have to be? Okay? I'm watching you talking, I guess. Rubbing your head and patting your belly at the same time. All right. Everybody follow? I can't do it. All right. So, center of oscillation. It's the point at which you would have to concentrate all of the mass so that the period of that resulting simple pendulum would be the same as the physical pendulum. Follow?
Yeah.
So, all you do is you say, all right, well, I know the period of my physical pendulum, right? We just found it. So how do I find the length of the simple pendulum? What's the equation for the period of a simple pendulum, you guys?
T equals 2 pi square root
L over G, right? So plug this in for your period and solve for L. Cool? And if you do that, you end up getting, what is it, 0.83 meters? Is that what I said the answer is? Follow, you guys? All right, questions? All right, the very last thing. I don't even know if I don't think we even need to do an example on this. So, do you guys agree that circular motion, like if I take Buzzy the bee and spin him around, this is still periodic motion, right? Is it simple harmonic motion? So it turns out it actually is, or it can be treated as simple harmonic motion in 2 dimensions. All right? For example, so look, Uniform circular motion. Remember, a circle can be written, if you write it, is your x and y coordinates. Your x is r cosine theta, your y is r sine theta, right? Remember, sine theta is just the same as cosine of theta plus pi over 2, right? So look, my x coordinate is simple harmonic motion, my y coordinate is simple harmonic motion, where your x and y max are both r, right? Okay? So here's my two equations. Here's my x equation, here's my y equation. All right? And if you want to visualize it, here's this. Maybe? Gonna work? There we go. Aha. No, you go away. Get bigger. All right, I don't know why there are two circles there. Oh my gosh, why is it being a pain? All right, so pick one of the circles, either the green or the red. All right, so if you look at the red circle, you can see that the motion of this red particle, you can see that the motion of the red particle horizontally is the exact same as this red particle attached to a spring, right? And vertically, I don't know why they didn't draw the springs on the vertical one, but it's the exact same motion, right? Okay? So you can, if you choose to, you can treat circular motion as simple harmonic motion in two dimensions, x and y.
So it's just like the separate like parts of the parametric are both like simple harmonic motion.
Exactly.
Okay.
Exactly correct. All right, does that make sense, you guys? Okay, cool. Questions? All right, I believe that's everything.